Your brain is lying to you. The double slit experiment proves it. The stripes are knife-sharp, humming like hell breath. You flip on a path detector and they die. Two blunt bands where waves once sang. Same source, same slits. One sin. You tried to know. Your observation doesn't just reveal reality, it creates it, or kills it. That's the chill. In quantum labs, observation isn't eyeballs. It's any interaction that leaves a record. Air, heat, a stray photon. In minutes, we'll choose the ending after the scene is shot. Delayed choices, erasers that make yesterday feel negotiable. To see why a look matters, we have to go back to the slit that wouldn't behave. The experiment that refused to behave. Dim the room. London, 1801. Thomas Young stretches a card with two slits and lets light spill through. On the wall, bright, dark, bright, interference fringes, the signature of waves. Water does it. Sound does it. Light apparently does it too. For a century, that felt settled. Then 1905, Einstein's light quanta crashed the party. In some experiments, light hits like particles, photons. Two identities, one thing. By the 192s, the shock deepens. Electrons, the pinpricks of matter, diffract and interfere. You can feel the floor tilt. Waves and particles aren't species. They're stories hardware tells. Now it's personal. You're a grad student aligning an electron double slit. You choke the beam to a trickle, one electron at a time. Dots appear, lonely freckles on a phosphor screen. Come back an hour later, the freckles have conspired into stripes. No crowd behavior. Single arrivals still built interference. The line you write, each electron interferes with itself, feels like a confession, not an explanation. You push. What if you learn which slit a given electron used? You mount tiny detectors near the slits. Polarizers, beam splitters, current-sensitive wires, anything that couples enough to tag a path without a shove. The stripes vanish. The screen fills with two fat humps, as if you fired pellets. Turn the detectors off. Stripes return. You try gentler couplings. Still gone. The lesson bites. It isn't disturbance, it's knowability. What counts as knowing? The notebook gets messy. If a whisper electromagnetic coupling is enough, then the lab is littered with accidental observers, air molecules, thermal photons, table vibrations. Maybe looking is just the world leaving a mark, but the precision stings. With path info available, you don't get a bruised interference pattern. You get a clean sum of two single slit spreads. A toggle, not a smear. You tune detector efficiency, so only some electrons are tagged. The data split like a clean coin. Events with path info contribute to humps. Events without path info contribute to fringes. Fractions match the detector's success rate. No electron both leaves a tag and helps a stripe. The categories don't mix. That sharp line nags more than any slogan about mystery. Meanwhile, the literature piles on. Photons, electrons, neutrons, even C60 Buckyballs. Untouched, they build fringes. Leave which path information in principle, fringes die. In principle sounds philosophical until you breathe wrong. One night you forget to pump down. Morning gauge reads high and the stripes are gone. You exhale near the beam line and watch visibility sag. Air is a measuring device with no display. Scattered molecules entangle with the path. No person learns anything. The possibility that a record could exist is enough. You test polarization. Put identical polarizers before both slits. Interference lives. Rotate one by 90 degrees. Each path now carries a different polarization label. Interference dies. Add a downstream analyzer that erases the difference. Mix the alternatives back into indistinguishable states, and the fringes return inside the properly sorted subset. On the raw screen, still humps. In the coincidences that respect your eraser, stripes bloom. You didn't repair damage, you removed the label. Coherence becomes the word you circle. It's the quiet phase relationship between alternatives that lets amplitudes add and cancel. Detectors don't just sense, they correlate. They entangle the electron's path with another system, a tag. When tag states differ, the full quantum state holds the paths on separate ledgers. Cross terms don't contribute because the math respects the bookkeeping. Add amplitudes when histories are indistinguishable. Add probabilities when they're not. You rewrite your language. Instead of the electron is a wave, you say. The state evolves along alternatives whose amplitudes can interfere if nothing correlates those alternatives with readable marks. Instead of, we looked, so it chose, you say, we created correlations that made the alternatives distinguishable, so interference terms can't contribute. The story feels colder and cleaner. but one bruise remains. Even with the logic of labels, why does any single dot hit exactly where it hits? Why that bright fringe, not the dark? Next to it, the equations give distributions. The lab gives a point. You stare at a spec and write what every physicist writes at 1 a.m. When does possibility become fact? The next afternoon, your mentor drops a thin paper on the bench. John Wheeler's delayed choice. Build an interferometer that lets you decide wave-like or particle-like behavior after the photon is already committed to both paths. It reads like a dare. If causality is safe, timing won't matter. If our questions retroactively shape what the past even means, you'll feel it. You glance from the beamline to the clock and feel the floor tilt again. Hidden in your margin is a warning you won't forget. Language will try to run the show. It'll say the particle knew, or you changed the past. The apparatus will say something stricter. Your design decides which correlations exist, therefore which stories your data can support. And the next experiment will ask whether that choice can arrive last. Delayed choice, messing with causality. Wheeler's dare starts with cleaner plumbing. Trade the slits for a Mach-Zehnder interferometer. 150 beam splitter launches a photon into two paths at once. Mirrors steer them. A second beam splitter either recombines them to make interference or, if removed, keeps them separate so each path maps to its own detector. With the second splitter in, one detector goes bright, the other dark, depending on path length difference. Pull it out and click split like you had tiny bullets picking one arm. Now twist the knife. Decide whether that second splitter is present after the photon has already passed the first splitter. Put an electro-optic switch in the recombination region. Drive it with a fast, random signal. Cosmic photons, a high-speed QRNG, so the choice happens at the last microseconds, space-like separated from the source. You promise yourself you won't let language cheat. No, it knew. Just apparatus and timing. Run it live. When the second splitter is inserted, the dark port stays quiet and the bright port fires, just as if the photon traveled both paths and recombined. When it's yanked out, clicks show up at both ports with probabilities set by which path was taken. The surprise isn't the patterns, you predicted those. It's their obedience to a decision made too late to feel comfortable. Your last second switch lines up with whether the earlier segment is even describable as wave-like or particle-like. It lands like an accusation. What did the photon do before you chose? Here's the restraint the apparatus demands. You didn't change the past. No record existed of a path before your choice. No film reel was rewritten. What you changed was the joint question the whole experiment asks. With the second splitter in, you ask the world to reveal interference between two indistinguishable histories. With it out, you ask for which path correlations. Those are different questions with different allowed answers. The data refuse to support hybrid stories. You try to outsmart the setup. Leave faint which path tags along the arms. Tiny polarization rotations, weak scatterers, too small to obliterate interference on their own. Then choose the second splitter late and see whether something earlier bleeds through. But faint tags are still tags. With the splitter end, the interference contrast drops exactly by the amount of leaked distinguishability. With it out, the which path clicks sharpen by that same amount. The trade-off tracks a number, not your schedule. Timing games don't beat Knowability's bookkeeper. You stretch the geometry to the sky. Wheeler's cosmic version uses a quasar lensed by a galaxy, two routes a galaxy apart that still meet at your telescope. Your instrument can either recombine the routes to reveal fringes or keep them separate to read which image the photon took. Your choice happens now. The light left that quasar billions of years ago. If you recombine, you see interference that depends on phase differences laid down across intergalactic distances. If you separate, you register which route. It's not that your late decision rewrote a billion-year journey. It's that the only consistent stories your data permit are the ones matched to your measurement context. Switch perspectives to keep your footing. Think amplitudes. The photon evolves along two coherent alternatives until you change the unitary map at the end. Inserting the second splitter mixes those alternatives and allows amplitudes to add. Removing, it keeps them apart, so you add probabilities. Wave and particle aren't states the photon wore. They're summaries of what the entire apparatus plus evolution asked of it. You test the firewall against paradox. Could someone stationed near the first splitter learn in real time which setting you'll pick downstream by watching local clicks or fields? No. Local statistics are blind to a distant setting. The influence shows up only in correlations revealed when both sides' data are compared. That's the guardrail that keeps the story causal. No faster-than-light messages, no time travel hacks, just joint patterns that refuse to be classic. Labs get ruthless about the timing. Electro-optic modulators switch in nanoseconds. Random choices are generated fast and independently. Path lengths are balanced, so the photon spends as little time as possible in indecision. Space-like separation is engineered, not assumed. Papers stack up with the same verdict. Your choice sets the question. The past stays a ledger without a single narrative until the question is fixed. A human beat sneaks in. At 2 a.m., you stare at a live S-curve that flips between interference and particle-like counts as a random bit stream drives the splitter. You feel the tug to say the photon waited for you. You write a note instead. Choice selects correlators, not histories. You underline it twice. Then someone drops a rumor with teeth. Don't just choose late. Mark which path earlier, then erase that mark later after the signal photon has already hit the score again. The delayed choice quantum eraser sits there like a dare. What if yesterday's labels can be made irrelevant tomorrow? Quantum eraser. Information is the villain. The rumor isn't hype. Scully and Drew sketch it in the early 80s. Don't kick the particle, just tag the path gently and see if the mere availability of that tag kills interference. Then later, scramble the tag so the paths become indistinguishable again, and check whether fringes can reappear. Not on the wall, but hidden in carefully paired events. The villain wouldn't be force, it would be information. Kim's 1999 version turns the idea into wires and glass. Use a crystal to spit out entangled photon pairs. Call them signal and idler. Send the signal straight to a screen where it lands now. Route the idler through a maze of beam splitters and mirrors that either preserves which path labels or erases them by recombining options into the same downstream states. Critically, the idler's journey is longer. The screen dot shows up before you've decided what to do with the idler's tag. Run it, and the raw screen is a letdown. 2 bland humps, no stripes. Then you do the forbidden thing. You slice the data by coincidence. Group the signal's dots that coincided with idlers detected in the eraser outputs, where the 2 idler paths are indistinguishable at the end, and interference patterns bloom inside those subsets. 1 set of fringes in 1 eraser channel, a complementary, phase-shifted set in the other. Group the dots paired with idlers that carried which path marks, and you get no fringes. Add everything together, and the stripes vanish again into 2 humps. It feels like sleight of hand until you accept the rule. Interference belongs to indistinguishable histories, and coincidences are how you pick them out. The stakes are surgical. The signal photon never met a clumsy probe at the slits. All the path information lived in correlations with its idler. When the idler optics keep those correlations readable in principle, the signal's alternatives can't interfere. When the idler optics erase distinguishability by mixing the idler's path labels into the same final state, the signal's alternatives are allowed to interfere, but only inside the coincidence classes that respect that mixing. Translation: if a label could exist, your stripes die. If the label is truly gone, they can live again, but hidden in the right pairing. Language tries to run away. No, you didn't change a dot already printed on the screen. The signal hit before the idler even finished the maze. No message rides backward in time, and nobody. It's the cleanest way to ask a precise question. Among the events where the idler left no readable path label, do the signal's alternatives show phase-sensitive addition? The answer is yes. Every time you built that indistinguishability honestly. Push the dial to partial marks. Rotate polarizers by a few degrees, so the idler's 2 path states aren't orthogonal, or tweak beam splitter ratio so tags are only partly readable. The contrast of recovered fringes slides continuously with how overlapping the idler states are. Full path knowledge kills interference. Partial knowledge dims it. Full erasure recovers only the fraction you truly erased. Beneath the lab notes runs a compact law. Visibility squared plus which path predictability squared stays bounded by 1. A human beat cuts the jargon. The first time you see fringes appear only after a database sort, your stomach drops. You scramble to rule out bias. You shuffle time tags. You flip labels. The eraser coincidences keep their stripes. The which path coincidences stay smooth. Add them together. The stripes. Cancel. The universe refuses to give you interference for free in totals. It doles it out only inside the questions you earned. So what exactly got erased? Not a scratch on a track. What was erased was the possibility, even in principle, of telling which alternative occurred. In the eraser arms, the idler's 2 potential markers are transformed into the same downstream state. So the full entangled state no longer carries a label that keeps the signal's alternatives on separate ledgers. When labels match, amplitudes add. When labels differ, probabilities add. The screen's dot is part of a 2-photon sentence either way. Don't forget the guardrail. None of this enables faster than light communication. The screen alone is always boring. Only joint comparisons reveal fringes, and those comparisons require classical coordination. The no signaling rule stays intact because local marginals don't budge with your distant eraser choice. Then the villain grows fangs. Replace controlled optics with the room. One stray scattered photon can carry a path label into modes you'll never see. If in principle you could catch that photon and interfere it, you can design an eraser and resurrect stripes and coincidences. If the label disperses into countless thermal modes, the door slams. Decoherence spreads witch path information so widely that erasure becomes astronomically impractical. The environment is a giant witch path detector with no readout and no undo. This is the edge where the story sharpens. The double slit's mood swings aren't about conscious attention. They're about correlations that make alternatives distinguishable. The eraser isn't forgiveness, it's accounting, removing labels so histories can mix again. You start to see measurement not as a magical event, but as a coupling choice. Build tags and you get facts. Starve tags and you get stripes. But that leaves a sore question staring back from a single dot. If measurement is entangling and decoherence is environmental bookkeeping, when exactly does a maybe become a fact? To chase that, you have to ask what a measurement really is. What counts as a measurement, really? We've been blaming information. Now we have to say what kind of information turns a maybe into a mark you'd bet rent on. 3 moves wear the same lab coat but don't do the same job: entangling, decohering, and measuring. If we mix them up, we'll keep mistaking bookkeeping for magic. Start with entangling. Any gentle coupling that correlates the system with something else builds a joint state. Before the coupling, an electron's 2 paths are coherent alternatives. After a path tag, the world looks like this, in words: left path with left tag plus right path with right tag. That superposition didn't disappear, it spread. Nothing has collapsed. You simply copied which alternative into a second system, even if that system is one spare photon or a current in a wire. Now watch what the tag does next. It leaks. The tag bumps air, shakes the mount, radiates a little heat, scatters stray light. Tiny couplings that multiply. Mathematically, if you refuse to keep track of all those degrees of freedom, the off-diagonal terms, the quiet phase relations that power interference, shrink towards 0 in the state you do track. That is decoherence. Phases don't die. They get smeared across too many partners to ever be reassembled in practice. Interference becomes a museum piece unless you isolate and cool like a maniac. Measurement adds one more ingredient: amplification into a stable, redundant record. Avalanche photodiodes drive a microscopic fluctuation into a macroscopic current. Photomultipliers cascade electrons into a thud your scope can see. Cloud chambers make ionization bloom into a silver line. The device is designed to tip an unstable microstate into one of a few macrostates, then splash that result into the room as heat and scattered photons. Redundancy is the point. Many fragments of the environment now carry partial, consistent copies of the outcome. That's why lots of people can check the same dot later without erasing it. So the latter is correlate first, let the environment smear phases, then amplify and broadcast. Stir those together and you get facts in practice. But here's the hard edge. Decoherence explains why you never observe interference between macroscopically different outcomes and why classical-looking probabilities show up. It still doesn't pick which outcome becomes your experience. The full quantum state after measurement contains branches for each alternative, stripped of mutual coherence by the environment. Your notebook has one line. How do we connect those two? That's the measurement problem, and it won't be solved by swapping observation with eyeballs. Space shrink as you dial up the coupling to a warm resistor. It's a volume slider on decoherence. No one looked. The resistor did. When you crank an amplifier and record a voltage that screams or 1, you've crossed into measurement. A robust many-copy mark exists, whether anyone reads it now or later. The environment doesn't smear in any old basis. It picks the one your coupling keeps asking about, the pointer basis. Position is a classic because almost everything couples to where stuff is. In optics, polarization can be a pointer basis. In qubits, it's often energy or the computational states your readout prefers. The environment keeps hammering the same question over and over. Where are you? States that answer in that language resist further spreading. Coherence between them dies fastest. That's why chairs don't smear and why a dust grain's position gets copied into sunlight and air from every angle. This is where objectivity sneaks in without metaphysics. Quantum Darwinism says outcomes become objective when many independent environment fragments carry the same record. Photons bouncing off a grain each hold a bit of its position. Different observers sample different fragments and agree because they're reading the same redundantly stored fact. That agreement doesn't need a single cosmic ledger. It needs lots of overlapping ledgers that match. If that's a measurement, where's collapse? Depends on your taste. Many world says there's no extra ingredient. All branches persist, walled off by decoherence, and your sense of chance is self-location inside one branch. Objective collapse says nature sprinkles real, random jumps. Rare for small systems, common for big ones, on top of unitary evolution. The jump makes the pick. Copenhagen keeps the focus on practice. The cut between system and apparatus marks where we apply the probability rule and update the state as a tool. Cubism moves the update into the agent's head. A measurement is an act, an outcome is an experience, and the quantum state encodes personal bets constrained by the Born rule. Bohm hands you definite particle positions guided by a wave. The apparatus funnels the guiding wave into non-overlapping packets, and the particle rides one, giving you a definite record. Labs don't wait for a referee. They engineer which basis gets monitored, which channels get suppressed, and how fast redundancy grows. Error-correcting codes are industrial quantum erasers. Measure syndromes that reveal which labels leaked without learning the data's value. Then repair before visibility dies. Weak measurements peck at a system, pulling out partial information while leaving enough coherence for second acts. Quantum non-demolition readouts choose observables that commute with what you'll ask later, dodging fresh labels. A small human moment pins it down. You're aligning a camera on a single photon source, the counts look jumpy. You slide in a neutral density filter to test for saturation and watch the count statistics change shape from Poisson-like to something with fat tails. The filter added nothing mystical. It changed the chain. Correlations, leakage, amplification. Your log reads, new pointer, new records. It's dry. It's the truth. So what counts as a measurement? Any coupling that drives a microscopic variable into a macroscopic redundant record in some pointer basis, with decoherence making reversal hopeless in practice. Your eyes aren't special. Your retina is a warm detector array, plugged into a brain that updates beliefs after the room has already written the outcome everywhere. That leaves one open loop we can't dodge. If the world can smear possibilities into classical-looking spreads without picking, who or what picks the line your notebook ends up with? The fight over that question isn't in the optics. It's in the interpretations waiting outside the lab door. The big interpretations cage match. The lab gives you two rails: smooth unitary evolution that spreads possibilities, and blunt, definite outcomes that show up as dots and clicks. The math is one line. Your notebook is one line. Bridging them isn't a calculation. It's a choice about what you think those symbols stand for. 5 camps walk into the ring and promise the bridge in different voices. Copenhagen steps forward like a seasoned engineer. Use the quantum state to compute odds for outcomes given the setup you built. When the apparatus counts, update the state, collapse, as a rule for making the next prediction. Don't turn the wave function into furniture. It's a tool tied to the context. The cut between system and apparatus is where the probability rule bites, not a metaphysical border. Strength: ruthless focus on what experiments ask and answer. Weakness: where's the cut exactly, and why this outcome instead of that? Copenhagen shrugs and says physics is about what we can say about experiments, not about hidden machinery you can't probe. Many worlds refuses the cut. The wave function is the furniture, everything, and it evolves unitarily, always. Measurement is just entanglement, plus decoherence. Branches split when the environment kills coherence between macroscopically distinct alternatives. Each branch contains a definite outcome. You never see crosstalk because decoherence quarantines branches like soundproof rooms. Upside: no special rules for measurement, no vagueness, elegant continuity from micro to macro. Cost: probability. If all outcomes occur, why should squared amplitudes feel like odds? Advocates say rational agents inside branches should weight bets by squared amplitude. Critics say that sneaks the rule in. Existential price tag: an immense multiplicity you never sample directly. Cubism pulls out a notebook and moves the whole game to the agent. A quantum state encodes your personal betting commitments about experiences you'll have when you take actions on a system. Measurement is an action. An outcome is an experience. Updating the state is updating your beliefs given new experience. The Born rule is a normative constraint, not a physical law about waves and stuff. Beauty: it dissolves Wigner's friend friction. Wigner and the friend can hold different states for the same lab without contradiction, because states are about their different bets. Rub: some want a story about what exists independently of any agent's beliefs. Cubism won't deliver that. Bohmian mechanics puts particles back on the table. The Beebles are positions that always exist. A pilot wave, the wave function, lives on configuration space and guides those positions by a deterministic equation. In a double slit, the particle goes through one slit, while the full pilot wave passes through both and steers the trajectory into fringes. Measurement is just the apparatus becoming entangled. The guiding wave splits into non-overlapping packets. The particle rides one packet, giving a definite record. No measurement problem, only dynamics. Price, non-locality is baked in. The guiding equation depends on distance settings instantly. Bell already told you some non-locality is unavoidable. Reconciling Bohm with relativity is hard work, but ongoing. Objective collapse adds a new term to the law. Grashcake and its cousins stipulate random, rare collapses that hit more often as systems grow big. Microscopic superpositions can live long. Macroscopic ones die fast. Penrose and Diósi flirt with gravity as the trigger. Superposed mass means fuzzy space-time. Nature picks one branch in a time set by gravitational self-energy. Payoff, a clear mechanism that chooses a single outcome and predictions that, in principle, deviate from pure unitary evolution. Cost, you must fix collapse rates and length scales, guard energy bookkeeping, and face experiments that keep squeezing the allowed parameter space. Where do they stand in your lab? Copenhagen speaks the dialect of daily practice. Define the question, compute odds, update, move on. Many Worlds explains why decoherence makes macroscopic facts robust and why interference vanishes in practice without any extra jump. Cubism tells you why different observers can carry different state assignments until they compare notes, and why that is an inconsistency. Bohm draws the flow field you see hinted at in weak measurement streamlines and lets you picture dots as guided rather than born. Collapse theories tell you why your cloud chamber tracks look classical, even if you isolated everything. Nature's stochastic tap ensures it. Stress tests with the stories we've already lived. Delayed choice? Copenhagen? The question changes at the end, so the state you use changes. No paradox. Many worlds, branches are fixed by the whole unitary evolution. Your late choice picks which basis reveals which branch structure. Cubism. You alter your bets at the moment you act. The timing lives in your ledger, not in the world's past. Bohm, the pilot. Wave's global shape depends on the full setup. The particle's path reflects that without time travel. Collapse. If a real collapse occurred early, later recombination is already off the table. Eraser, Copenhagen. Erase distinguishability and interference can show in the right coincidences. Many worlds. Post-selection picks subbranches where phases line up. Cubism. Conditionalize on the idler outcome and your updated beliefs show fringes. Erase restores overlap of guiding waves in configuration space. Conditioned trajectories show fringe structure. Collapse. If spontaneous hits didn't happen, erasure logic holds. If they did, coherence is gone. Bell, Copenhagen keeps it operational. Quantum predictions beat local realist bounds. No signaling survives. Many worlds points to global entanglement structure. No spooky influence inside a single space-time branch. Just correlations written in the wave function. Bohm nods. Non-local pilot wave guidance is the mechanism. Still no messages faster than light. Cubism says agents must structure expectations to match those correlations. The impossibility of signaling remains a rule about what any one agent can do. Collapse models typically inherit non-local features to match the data. A microbeat from the hallway. Two grad students argue at a whiteboard at midnight. One draws branching trees, the other draws pilot wave streamlines. They're talking about the same counts on the same scope. The debate trims how they think, not what they measure next morning. Here's the through line that keeps your hand steady. The lab never demanded a final metaphysics to work. It demanded discipline about questions, couplings, and records. Interpretations shape how you sleep and which paradox you pick fights with. But the devices sing the same tune. Preserve indistinguishability for stripes. Build redundancy for facts. If one day a levitated nanosphere fringes where collapse said it shouldn't, or decoherence breaks where it shouldn't, the cage match will end with data. Until then, pick the story that keeps you honest and keeps your screws tight. Wigner's friend, whose reality is real. 3 doors down, there's a sealed room. Inside, your friend measures a cubit prepared in a superposition. Call it up plus down. Her apparatus hums, a pointer twitches, and she writes in her notebook, result, up. For her, the fog clears into a fact. Outside, you treat the sealed room. Qubit, device, air, and friend as one quantum system evolving smoothly. Your ledger reads, friend sees up plus friend sees down, a coherent superposition of entire lab states. Same physics, 2 incompatible stories, both demanded by the rules, depending on who's carving the world. Now escalate. You, playing Wigner, don't open the door. You aim to test the whole room for coherence, as if the friend and apparatus were just another interferometer arm. In principle, if the lab stayed isolated, you could choose a measurement sensitive to the phase between friend sees up and friend sees down. See interference, and your superposition story was right, but your friend insists she already witnessed up. If both expectations land in their own domains, then fact isn't universal. It's tied to the cut each agent draws. Here's the catch. The math won't let you dodge. The predictions collide only if you try to fold them into a single global narrative with one set of absolute facts shared by all observers at once. Keep descriptions agent relative. Her update inside, your unitary outside, and each set of bets pays off in its proper arena. Force them together naively, and quantum theory pushes back. Frotchiger and Renner sharpened the point. They built an extended Wigner's friend scenario with 2 labs and 2 outside observers. Assume 3 things. That quantum mechanics applies universally, even to labs and observers, that there's a single world with single outcomes, and that agents can consistently reason about each other's inferences. Stitch those assumptions into one master story, and you get a contradiction. Not a taste problem, a logical clash. Something has to give. The universality, the single world, or the idea that everyone's inferences cohere into one shared ledger. Take a breath. This isn't laboratory theater for humans on turntables. It's about what counts as a fact before records are redundantly imprinted into the environment. Once a pointer state has leaked into millions of photons, facts go public. Before that leakage spreads, there's still room, on paper and in small photonic analogs, to keep coherence around friend plus notebook memories and test Wigner-style interference. Simple versions have been built with qubits acting as friends, showing that what looks like a definite record inside can still be part of an outside coherent description until decoherence locks it down. Interpretations line up again with different bills to pay. Copenhagen says facts are contextual. The friend has a fact relative to her apparatus. You have a superposed description relative to yours. Don't fuse incompatible contexts into one meta account. That's a category mistake. Many world shrugs. Both friend sees up and friend sees down, live in separate branches. Your interference test only works if you reverse the branching before decoherence grows fangs. If you can't, that's a practical limit, not a conceptual one. Cubism grins. Quantum states are personal betting books. The friend's update to I saw up is hers. Your superposed state for the lab is yours. No contradiction until agents interact and exchange records. Agreement is what happens when ledgers sync through communication, not what exists beforehand in a God's eye diary. Bohmian mechanics takes another route. Particle positions are definite. The friend's pointer points somewhere. Your ability to see interference is about the pilot wave's phase structure, not about erasing her experience. Non-local guidance keeps the expectations aligned without global contradictions, though stitching this cleanly into relativity is a hard climb. Objective collapse tries to end the game early. If large systems truly undergo spontaneous collapses, then your lab-level interference test fails well before you can probe coherence. The friend's outcome becomes an objective event, written into the world by law. Your superposition of labs never lived past microscopic scales. That's testable, which is why experiments keep pushing coherent control of bigger systems to see if they hit an unforeseen wall. A small, steel-edged moment in a seminar room makes it human. A student asks, "So where are the facts, really?" The speaker points to the environment. In the redundantly recorded bits, photons, phonons, electrons, that many observers can sample independently. She frowns. And inside the sealed lab? Facts for the friend relative to her cut, he says. If Wigner hasn't let those records leak, his cut still allows coherence. She scribbles, then circles a phrase. Facts are where redundancy lives. That's the practical compass. The environment writes facts by copying outcomes widely. Before that copying, different agents can hold incompatible, yet internally consistent quantum descriptions without anyone being wrong. After redundancy blooms, those descriptions converge because everyone's sampling the same copies. The cost is giving up a simple, absolute list of facts that exists for all cuts at once. The benefit is a map that matches both our equations and our experience. The double slit trains you to ask what is indistinguishable and for whom. Wigner's friend takes that instinct to people and rooms. Indistinguishability at the edge of records means interference can, in principle, reappear. Distinguishability via environmental copying means outcomes go public. If you want a single world with single facts, you must explain how and where that copying happens, or add a law that picks a branch. If you're content with branches or with agent-centered ledgers, the paradox softens. Meanwhile, across town, correlations at a distance are waiting. Bell will lean in and cut off a whole class of hidden scripts, and he won't whisper. Non-locality. Without messaging. Bell's thunderclap. While the friend debate simmers, a sharper blade lands in 1964. John Bell asks a simple, unforgiving question. If outcomes are fixed by hidden instructions carried locally with each particle, and nothing influences anything faster than light, what correlations are possible? He turns that into inequalities. If nature breaks them, local hidden scripts are out. Build the stage. Create pairs in an entangled state and send them to distant stations, Alice and Bob. Each picks a setting on the fly, polarizer angles for photons, measurement axes for spins, and records a binary outcome. Repeat thousands of times. In any local hidden variable model, a certain combination of correlations stays bounded. That's Bell's inequality. Quantum mechanics, using entanglement's amplitudes, predicts stronger, structure-rich correlations that can cross the bound without enabling messages. The stakes are blunt. If experiments violate Bell's bound, you can't keep both locality and the idea that results were fixed all along by shared instructions. And there's a catch. To trust a violation, you must close loopholes. Detection inefficiency, biased samples, slow or correlated random choices, or time windows where a subliminal whisper could conspire. You can salvage one only by bruising the other, or you can change what you mean by reality to something relational or branch-filled. Action moves in the 198s. Alana Aspects group switches polarizer settings while photons are in flight. Correlations step over Bell's line in the way quantum theory predicts. Skeptics point at loopholes. Maybe only friendly photons were detected, or the choices weren't independent or fast enough. Labs keep tightening bolts. Source brightness climbs, detectors get efficient, electronics race faster. Then, 2015, a string of Loophole-Free tests in Delft, Boulder, Vienna. Choices generated randomly and quickly. Stations spaced far enough that light can't connect them in time. Detection efficiencies high enough to cut off bias. The S-value, a compact version of Bell's bound, climbs past 2, nudging 2.4, 2.6, 2.7 as quantum expects. Later, teams use cosmic photons to pick settings, pushing any conspiracy back billions of years. The verdict doesn't budge. A microstory puts a pulse in it. A postdoc wheels 2 optical tables to opposite ends of a corridor. QRNGs blink, counters tick. The live S-plot pushes past the classical ceiling. He texts his mother. It's non-local. She sends a heart emoji. He laughs, then adds under his breath, "But I still can't call you faster than light." Here's the guardrail. Even with Bell-violating strength, no one can use entanglement to send a message superluminally. Alice's local statistics don't change when Bob flips his setting. Bob's don't change when Alice flips hers. The extra lives only in joint correlations revealed when they compare notes later. That's the same firewall you met in delayed choice and erasers. Local marginals are dull. The fireworks live in the paired ledger. Interpretations line up to pay the bill. Bohmian mechanics nods. Non-locality is in the pilot wave's guidance, instantly shaping outcomes across the pair in a way that preserves no signaling. Many worlds points to the global wave function's entanglement. The non-locality lives in that global structure, not in space-time arrows of influence. Copenhagen keeps it operational. The formalism gives joint probabilities that beat Bell. Don't demand hidden local furniture. It never promised. Cubism reframes it. Bell constraints are rules for an agent's consistent bets about joint experiences. No agent can exploit them for signaling. Objective collapse models, if they match the data, typically inherit non-local features too. Now tie it back to your stripes. In the double slit, you added amplitudes from indistinguishable alternatives for one particle. In Bell tests, you add amplitudes across alternatives of 2 systems together. The joint state doesn't factor into separate stories. Forcing a local hidden script is like insisting each slit carried a tag all along. It kills the interference that builds the correlations. Nature seems to say, if you want entanglement's power, you must accept correlation bookkeeping that isn't confined to neighborhoods, while still respecting the no messaging line. A hallway question keeps showing up. If there's non-locality, why can't I flip a switch here and flash a dot there? Patient answer. Because quantum mechanics aligns joint outcomes, not single-side rates. To exploit that, you need classical comparison, light speed or slower. Cryptographers smile at this. Eavesdroppers can't fake those joint patterns without leaving scars, and they can't pluck information from one side stream alone. Bell doesn't end the foundation fights, it narrows them. Keep locality and you'll abandon naive realism about pre-existing outcomes. Keep realism and you'll swallow non-locality. Keep both by reshaping reality into something relational or many-branched. Whatever you pick, the lab's verdict is clean. The world's correlations outrun classical stories, but they never hand you a faster-than-light phone. And inside the lab, the message is practical. Entanglement isn't a vibe, it's a resource with constraints. You can violate Bell, secure keys, and steady sensors and still sleep under relativity's ceiling. The thunderclap is loud because it's precise. It told you exactly which classical stories to stop telling, and exactly how far quantum can go without breaking causality. Rebuilding the double slit from the ground up. Let's clear the table and rebuild the double slit without mystic varnish. Start with 3 pieces you can hold in your head. A source that prepares a quantum state, a set of alternatives that state can traverse, and detectors that turn possibilities into records. Everything else, wave, particle, observer effect, is shorthand for how those pieces are wired together. At the source, you don't mint tiny bullets. You prepare a state with non-zero amplitude for at least 2 alternatives. Call them L and R. Quantum's engine is arithmetic with rules. Add complex amplitudes for alternatives that are indistinguishable to the full apparatus plus environment. Then square to get probabilities. The interference term lives in that add then square. Kill indistinguishability and you replace amplitude sums with probability sums. Stripes collapse into humps. Walk the paths. Each slit is a spatial mode, each arm an option. If nothing correlates L versus R with any other degree of freedom, the joint state reaching the screen is effectively L plus R, and the detection probability includes the cross term to re, psi-L, psi-L, psi-L. That cross term is the stripe maker. The moment a tag gets attached, polarization twist. Scattered photon. A tiny current in a wire. The joint state becomes L tag low plus R tag gray. Compute probabilities for the screen alone by tracing over tags and you multiply by tag low, tag R. If that overlap is 1, stripes live. If it's 0, they die. That overlap is your practical knowability knob. Detectors aren't mystical umpires. They're engineered amplifiers that drive a microscopic correlation into a macroscopic redundant record. A pixel doesn't decide. It avalanches, dumps heat, sprays photons, and writes the outcome into thousands of environmental fragments. By the time you walk in, the room already knows where the dot is in the only sense that matters for physics. The information is out, copied, and hard to reverse. Strip the language down. Instead of saying, the particle went through both slits, say, the state evolved along alternatives whose amplitudes can interfere because no distinguishing label existed. Instead of, we looked, so it chose, say, our apparatus built correlations that made the alternatives distinguishable, so cross terms couldn't contribute. Instead of, the universe cares if we know, say, the joint state cares, whether a label exists in principle that could be read. A lab moment fixes it in your bones. A grad student dials up a clean fringe with cold atoms, then leans in to tweak a shutter and breathes, barely, on the flight region. Visibility drops. The pump's pitch shifts. CO2 and water vapor become roaming tags. The effective tag out slides towards 0. She pumps down, cools the chamber, stripes crawl back. The note is dry. Breath kill coherence, but it's the whole theory in one line. The environment is a measuring device with no display. Where does non-locality fit? In single particle interference, it doesn't need to. Everything happens within one system and its nearby environment. Non-locality roars in when you use entanglement. Then the add amplitudes rule spans multiple stations, and Bell's correlations appear. The woe is real. The loopholes aren't. The guardrail holds. Local statistics stay blind to distant knob settings. Interference and entanglement are the same arithmetic, stretched across different cuts. Now pay off some earlier loose ends. Quantum erasers don't resurrect a damaged pattern. They remove labels so the right subsets of histories become indistinguishable again. That's why you only see fringes inside coincidences that respect the eraser optics. Delayed choice doesn't rewrite the past. It finalizes which question the apparatus asks of the entire evolution. Weak measurements dim stripes by installing partial labels. Quantum non-demolition readouts ask questions that don't inject new labels into variables you'll probe later. Every trick is label management. Collapse in this rebuild is bookkeeping. The unitary evolution creates or preserves coherence. Uncontrolled coupling smear phases across environments. Amplification prints redundant records. After that, treating the system alone as a classical mixture is accurate for every practical purpose because the off-diagonals are effectively 0. Whether you add a literal stochastic jump, collapse models, keep all branches, many worlds, anchor reality to particles guided by a wave, Bohm, or treat the state as an agent's betting book, cubism. The lab arithmetic doesn't change. Preserve indistinguishability to get stripes, build redundancy to get facts. A microstory drives the point home. You're aligning a Talbot-Lowe interferometer for heavy molecules. A faint, periodic pattern appears, then fades every time a nearby vacuum gauge cycles its hot cathode. That glow is a label factory, thermal photons tagging paths. You wrap the gauge, gate its duty cycle between shots, and the pattern returns. You didn't persuade molecules to be waves. You stopped them from being labeled. Here's the clean checklist you carry forward. Indistinguishable alternatives. Add amplitudes, interference possible. Distinguishable alternatives. Add amplification plus a veil. Add probabilities, interference suppressed. Amplification plus environmental copying, redundant records, facts and practice. Post-selection, carve data into questions that match where indistinguishability was preserved. That's the rebuilt double slit. No mysticism, no special role for eyes, just apparatus setting what the world can say back. And once you see it this way, a persistent rumor loses oxygen. If minds aren't needed to flip waves into particles, should we retire the idea that consciousness collapses the wave function? Or is there any corner left where a look does something no detector can?
Does consciousness collapse the wave function?
The rumor wears good cologne.
Maybe minds collapse waves. Von Neumann noticed you can push the measurement chain outward, system to detector, detector to environment, environment to brain, and nothing in Schrödinger's equation forces a stop. Wigner added a nudge. Perhaps conscious experience is where collapse happens. It's tidy, it flatters us, it also walks into a lab that doesn't need it. Run the chain in real hardware. A single photon hits a photodiode. An electron avalanche explodes through the junction, dumps heat, sprays infrared photons, shakes the package. That cascade imprints click into thousands of environmental modes. By the time retinal opsins or a camera sensor see anything, redundant records already carpet the room. If consciousness collapses, it arrives late to a scene the environment has already locked down. People still go looking. Teams compare detector counts when participants attend versus ignore or meditate or drift. Once you control for drift, temperature, and bias, the rates don't budge. Meanwhile, tiny, mindless tweaks, tilting a polarizer by a degree, warming a substrate a few Kelvin, shift interference exactly as the coupling math predicts. The universe cares about Hamiltonians and overlaps, not about whether you're bored. The quantum Zeno effect gets enlisted as a loophole. Watch pots that don't boil. But watching here means rapid, repeated projective interactions that re-prepare the state. Lasers on ions, microwaves on spins, any apparatus can do it. Your attention isn't a Hamiltonian. Your hardware is. Freeze a decay with fast probes, and it's the probes writing constant labels, not a gaze doing metaphysics. Another lane swaps dynamics for grammar. Cubism says quantum states encode an agent's personal betting commitments. Measurement is an action, outcome, and experience. Relational moves say facts are relative to interactions. These shift where collapse lives, from world to ledger. But they still don't grant neurons a physical privilege. They explain why Wigner and his friend can carry different state assignments without contradiction. They don't require minds to trigger non-unitary jumps. The brainless quantum computer line tries a different door. Maybe cognition depends on long-lived, macro-scale coherence. But warm, wet tissue is brutal to delicate superpositions. We nurse at millikelvin. Microtubule proposals have been hammered by numbers. Decoherence times are catastrophically short, many orders too short for cognition. If tiny superconducting loops, sealed and frozen, fight to survive microseconds of coherence, Cortex at 310K isn't secretly running Mach-Zehnder logic. Audit every place observation mattered earlier. Double slit fringes vanish when which path labels exist in principle, whether or not anyone looks. Eraser fringes reappear inside coincidences, sorted hours later, even if no one ever reads the raw logs. Delayed choice statistics line up with late settings driven by QRNGs and sealed boxes. Bell violations show up between qubits sealed in cryostats. Swap a human for a robot for a relay for a lump of warm silicon. The numbers hold. Where minds do matter is where any detector matters. They're warm, noisy, and late in the chain. A microstory clears the fog. A team builds a sealed experimenter. A controller chooses settings, runs trials, stores results in encrypted memory. The room empties. Hours later, without anyone ever seeing the internal logs, the drive is zeroed. Only an external coincidence counter survives. The quantum correlations are exactly where theory puts them. The presence or absence of human awareness made no statistical dent. The only knob that mattered was whether which path labels were physically erasable. So what keeps the rumor alive? It answers a real itch. How does a smeared set of possibilities become this definite now? If you want a mind-centered solution, you can staple collapse to consciousness and declare victory. Then you owe machinery. Which features of experience cause collapse? Intensity, self-reference, language, how do those variables enter the dynamics? How do anesthesia and dreamless sleep work? Why do interference conditions care about a stray thermal photon you'll never reconstruct, but not about whether anyone's awake? The working alternative is less glamorous and more precise. Collapse in the lab is an update after amplification and decoherence have made a result, a public record. Decoherence explains why those records are stable and why reversing them is practically impossible. Interpretation split cleanly. Many worlds keeps all branches and lets self-location handle chance. Bohm keeps definite positions guided by a wave. Cubism keeps collapse in the agent's ledger. Objective collapse adds real stochastic jumps by law. None of these require a mental ingredient to match experiments we've run. They're still an honest frontier, just not where the rumor points. If
nature adds objective collapses, their fingerprints would show up as tiny deviations from unitary evolution. Excess heating, spectral broadening, lost fringes for massive superpositions that no state of mind can fake. Gravity might play referee. Penrose and Diósi sketched away. That's testable, which is why levitated nanoparticles, ultra-cold cantilevers, and macromolecule interferometers eat up nights in helium. So, does consciousness collapse the wave function? The clean answer from decades of data is no. Replace a person with a photodiode and the statistics don't flinch. Replace a gaze with a roomful of air and the stripes die exactly when the overlaps demand. Minds are passengers, not pilots, in this part of the story, and that's liberating. It means the observer effect you can build with your hands is the one that matters. Labels, overlaps, amplification, redundancy, while minds stay free to wonder without carrying the physics on their backs. Gravity, time, and objective collapse. If minds aren't doing the collapsing, maybe nature is, quietly, by law. That's the hunch behind objective collapse models. They add a real stochastic nudge to Schrodinger's smooth evolution. Rare for small things, frequent for big ones. So macroscopic superpositions die on a clock set by the world, not by us. Gravity is the most seductive accomplice. Penrose and Diósi frame it like this. Put mass in a spatial superposition, and you're superposing two different space-time curvatures. General relativity doesn't like fuzzy geometry. That mismatch stores a gravitational self-energy. The larger it is, the shorter the lifetime of the superposition. Roughly, heavier objects, larger separations, faster collapse. No observers needed, no apparatus, just mass, time, and a timer set by gravity's own bookkeeping. Translate that to a double-slit family. Photons and electrons, too light. The collapse time would be effectively infinite. But drag a nanoparticle, billions of atomic masses, into a two-path superposition a few micrometers apart, and Penrose-Diósi predicts it won't last long. If you can keep coherence past that predicted lifetime and still see interference, gravity-triggered collapse takes a hit. If you can't, and you've tamed every mundane leak, gravity steps forward as a suspect. Labs are quietly building the trap. Optomechanics chills tiny mirrors and membranes until their motion sits near the quantum ground state. You don't fling the mirror through slits. You create superpositions of vibrational states and watch for interference fringes in phase space. Any extra collapse shows up as excess dephasing or unexplained heating. Levitated nanoparticles push harder. Suspend a silica sphere in a light or electric trap. Cool its motion with feedback to a handful of quanta. Then release, split its wave packet with shaped pulses. Wait, and recombine. Every knob fights you. Gas collisions, blackbody photons, trap noise, Earth's rumble. Because each is a which path tag in disguise. The hunt is simple to state and brutal to execute. Make the world quiet enough that gravity's hypothetical whisper is the loudest remaining voice. GRW and CSL take a different path. They write collapse into the equation. Random, rare localization events with a rate and length scale tuned, so electrons stay quantum. Dust grains don't. Those parameters aren't decorative, they're testable. Collapse adds tiny jolts of energy, smears spectral lines by a hair, heats ultra-cold cantilevers by a whisper.
Experiments squeeze those corners. X-ray emission bounds the jump rate. Interferometry with atoms and molecules pushes the allowed length scale. Mechanical resonators cool to microkelvin, hunt for unexplained tremors. Each new limit tightens the noose without snapping it. Yet, a microstory shows the grind. In a basement lab, a team levitates a 100 Nament silica sphere in an optical cavity at 10 to the power of -11 Meribar. They spend months hunting stray light, damping floor hum, and mummifying hot electronics. One night, the feedback loop holds and the center of mass motion sits near the ground state longer than any run before. They release for a millisecond. Kick, wait, recombine. The contrast is thin but non-zero. They translate the dataset into a bound on CSL parameters. The subject line of the email is dry. RC, turn to the power of -7m, if lambda not back black bic, lambda 10 to the power of -8, s to the power of -1. The thrill is not. Gravity also shows up as time. Superpositions traveling along paths with different gravitational potentials tick at different rates. Gravitational redshift for matter waves. Atom interferometers measure these phase shifts cleanly, and so far unitary quantum mechanics plus general relativity's time dilation explains the data without extra collapse. Some proposals flip it. Maybe time itself, being read off imperfect clocks, induces fundamental difficene. Those ideas are crisp enough to test. So far, the phase bookkeeping lands on standard theory's side of the ledger. There's a thought experiment with cinematic pull. Put a tiny mirror on one. Arm of a Michelson interferometer. A single photon enters. If it takes arm A, radiation pressure nudges the mirror a hair. If B, the mirror rests. With ultralight mirrors, ground state cooling, and short pulses, the photon can entangle with two mirror states and, in principle, bring them back together. If interference survives, those mirror states overlap coherently. If an objective collapse hit, overlap died. Early versions were too warm and heavy. Newer designs creep closer, stealing tricks from qubit labs, squeezed light to beat shot noise, phononic shields to dam leaks. Objective collapse would redraw the map in a good way. It would turn the quantum to classical transition into a frontier with coordinates, mass, size, separation, time, and give the measurement problem a new constant rather than a new parable. But there's a cost. You must pick numbers. Too frequent, and electrons would blur spectra we've already measured. Too rare, and macroscopic superpositions would live longer than they do. Data already fences the viable region into a shrinking patch. If gravity stays quiet, the pressure shifts. Collapse models retreat. Decoherence plus interpretations without extra dynamics carry the load, and the border between stripes and facts looks purely environmental. If gravity speaks, an unexplained loss of contrast after every leak is killed, excess noise with the spectral fingerprint of random hits, then a new term enters the book of physics, and the double slit graduates from metaphor to meter for the new constant. Either way, the march builds tools we need. Vibration stacks that tame nanog rumble, cryostats that hush phonons, photonic crystals that starve radiative loss, quantum-limited amplifiers and squeeze states that shave readout noise. The same gear that corners collapse makes sensors sharper and processors sturdier. You go looking for nature's timer and come back with a better clock. What does this mean for our earlier itch? When does a maybe become a fact? If collapse is real, sometimes the world picks for you, on schedule. If not, facts arrive when redundancy does, and collapse is an update in a universe that keeps all branches or hides definite coordinates under a pilot wave. The next act doesn't settle it, it raises the stakes. How far can we push stripes up the mass ladder before either gravity or our patience blinks? Bigger, slower, stranger, scaling interference up. You feel the frontier the first time a heavy molecule draws a pattern nobody expected it to. Late 90s, Buckyballs, C60, then C70, sail through nanofabricated gratings. They're hot, jittery soccer balls of carbon, hundreds of atomic mass units. Yet the detector builds a periodic density, bright and dark, that only coherent matter waves can make. Nudge the source temperature up, the stripes fade, thermal photons whisper which path into the room. The lesson is blunt. Even fat objects interfere until the environment tattles. From there, the mass climbs. Chemists tape weights to molecules, functional groups, fluorination, aromatic scaffolds, marching into thousands of atomic mass units. Talbot-Lau interferometers make this doable. 3 gratings, carefully spaced. The first chops spatial coherence into a comb. the second diffracts. The third samples the self-image at the Talbot length, a distance set by de Broglie wavelength and grading period. It's interference without literal twin slits, but the arithmetic is the same. Indistinguishable multipath histories add, labeled ones don't. A lab beat fixes the cost. A student spends days baking chambers, tuning collimation, and cleaning sources. A faint fringe appears, visibility a few percent. She goes home. Night HVAC nudges the room 2 degrees cooler. A lamp ballast runs longer. Morning plots are flat. She tracks it to stray infrared, blackbody photons tagging paths. She wraps the ballast, gates heaters, and the fringe limps back. The note is dry. Ballast photons, which path? And true. Macromolecule dreams arrive, proteins, maybe viruses. The obstacles grow teeth, internal vibrations coupled to the outside. Big objects absorb and emit thermal light, like tiny stoves. Their de Broglie wavelengths at practical speeds are picometers, so interferometers balloon to meters. You need vacuum better than space, temperatures where glow turns to whisper, beamlines so quiet Earth's rumble looks like a label. Teams pivot from solid gratings to optical ones, standing light waves as phase masks, so molecules don't brush walls that would mark them. Pulsed, far-off resonance fields do the job without sticking extra labels. Levitated particles promise a different road. Trap a silica nanosphere with light or in a Paul trap. Feedback cool its center of mass motion to near the ground state. Then release and split its wave packet with shaped pulses, optical kicks, magnetic gradients, let it drift and recombine. If a 100 nanosphere can ride a 2-path superposition for milliseconds and show phase-sensitive return,
You've fenced off a swath of classical intuition. The checklist is brutal. Ultra-high vacuum, so one rogue molecule doesn't yell left mid-flight. Cryogenic shields so blackbody photons don't leak labels. Vibration stacks so building hum doesn't become a tag. Timing that threads gravity's pull with nanosecond honesty. Under the hood, the same numbers rule. Visibility tracks, tag-O, tag-R, the overlap of environmental states tied to each path. Big masses spew photons, overlaps shrink. You fight by cooling, by darkening optics, by filtering phonons with phononic band gaps, by shaping pulses that kick without leaving residue. You measure residual gas and compute decoherence rates from cross-sections. You count spectral photons to bound radiative tagging. Every knob is label management, scaled up. A micro-story catches the grind. In a basement, a group levitates a bead, 10 to the power of -11 magbar, cavity locked. The sphere jitters, then calms to a handful of quanta. They kill the trap. Kick back! The readout shows a sliver of contrast. Not art, but a line above noise that survives when they invert labels and shuffle time tags. They translate it into a bound on collapsed parameters and a memo to themselves. Floor rumble at 18 Hz imprints phase, add notch. Biology hovers at the edge. A protein beam is messy, shapes, charges, fragmentation. But the goal isn't pretty, it's principle. Can a floppy, warm molecule hold enough indistinguishability to draw a fringe before its own thermal life tattles? Teams propose cold sprays, gentle guides, all light gratings. Viruses get whispers in grant halls. The push isn't to be sensational, it's to test whether decoherence alone fences the border or a new law does. Every success squeezes objective collapse models, green murdered or CSL-style parameters that would nuke fringes at these scales get cornered. Every stubborn failure after a ruthless audit of mundane leaks, hands collapse a little air. Either way, you win. Engines built to hush the world become sensors that sniff vanishing forces and clocks that shave noise. Quantum tech feeds the climb. Frequency-stable lasers hold phase for hours. Squeeze states shave shot noise in readouts. Low-noise avalanche photodiodes count single molecules without baking them. FPGA timing tags events with sub-nanosecond precision so you can carve coincidences when fringe contrast is thin. Cryostats born for qubits now cradle molecules in beads. Photonic and phononic crystals starve unwanted channels. The human rhythm never leaves. On a good night, a histogram grows teeth. Someone whispers, "There." Then the room list leaks to retest. On a bad week, a pressure burst kills a month's run. Someone writes, "Gasket creep, which path?" You get used to victories that look like decimals. Here's the quiet point that ties it back. Scaling interference up doesn't make the paradox weirder, it makes it honest. You see, that observer effect is engineering. Managed labels and stripes live.
even for beasts you once thought classical by birth. Let labels bloom and humps return. No mysticism needed. Somewhere ahead sits a largest fringe we can coax. Or none at all, if gravity or spontaneous hits are waiting. Either way, the next machine you build will decide, one fragile cross-term at a time. From paradox to power, tech writing the observer effect. All those fragile stripes and traded labels didn't stay in the philosophy drawer. They became blueprints. The same rules that make a screen go bland unless you ask the right joint question are now the rules that let us compute, sense, and communicate in ways classical devices can't touch. This is the "this affects you" turn. Phones that navigate better, scans that see earlier, codes that thieves can't copy. Start with computing. A qubit isn't a tiny switch. It's a controlled superposition with phases you can steer. Gates entangle qubits, so their alternatives become a web of interfering histories. Good algorithms are choreography. You lay down many computational paths, then arrange interference so wrong answers cancel and the right ones add. Grover amplifies the marked item's amplitude. Shor uses periodicity, so factors pop as constructive peaks. The readout at the end isn't magic, it's a measurement that turns phase structure into bits. The hard part mirrors the slits. Keep unwanted labels out. Stray photons, phonons, flux noise. Each is a witch path tag by another name. Quantum error correction is the industrial eraser. Encode across many qubits, measure syndromes that reveal leaked labels without learning the data, and actively erase them before visibility dies. Overhead is heavy. The payoff is a machine that uses add-then-square arithmetic as a resource. Sensing leans even harder on fragility. If distinguishability kills interference, then tiny influences that nudge phase become detectable if you keep coherence alive. Atom interferometers split and recombine matter waves to measure gravity and rotation. The phase shift is your turn.
Signal. Superconducting qubits do Ramsey and spin echo to sniff faint fields. Quantum metrology squeezes uncertainty. Entangle many spins so phase noise drops below the standard quantum limit. Weak measurements play careful thief. Partial tags that extract information while leaving enough coherence for a second pass. Quantum non-demolition readouts ask questions that don't write new labels on the variable you care about. Even LIGO's upgrades use squeezed light, engineered fluctuations, to cut shot noise. The observer effect becomes a dial. Coupled just enough to learn, not enough to label away your stripes. Communication turns witch path tattling into a burglar alarm. In BB-84, Alice encodes bits in non-commuting bases. Any eavesdropper who observes in the wrong basis leaves a disturbance you can spot. No cloning is the slit logic in disguise. You can't copy an unknown state without creating labels that change its interference relations. Entanglement-based protocols go further. Share pairs, test Bell correlations. If the S value stays high, no local hidden adversary can be faking your link. Device-independent schemes lean entirely on those inequalities to certify security, even when hardware can't be trusted. The no-signaling guardrail isn't a nuisance, it's a shield. An eavesdropper can't hide in the marginals. She must touch correlations, and touching leaves scars. Imaging learned to cheat too. Ghost imaging forms a picture of an object using a detector that never sees it, by correlating a twin that did. Interaction-free measurement exploits the same logic as fringes lost by knowability. Set up an interferometer with a dark port, then place a sensitive object in one arm. The mere possibility of which path information brightens the dark, letting you detect something you tried not to touch. Quantum illumination uses entanglement to get a modest edge in finding a weakly reflecting target in noise. The idler's retained correlations help you pick signal out of soup. Each trick is a story we've told already, just flip toward work. Under the hood, everything is label management. You pick a pointer basis by design, you isolate and cool to keep tag-o-tag-r near 1 where you want interference, and you drive strong, redundant records where you want measurement. You schedule erasers, error correction pulses, faster than the environment can carve labels. You engineer environments, phononic band gaps to starve vibrations, photonic crystals to drown radiative loss, Purcell filters to drain unwanted modes. You lean on quantum Darwinism for readout. Redundancy makes facts objective for many users, and starve it inside computations, so phases stay private. A micro-story ties the loop. A team runs a small surface code patch overnight. Logs show a burst of correlated errors at 3:12 a.m. They trace it to a refrigerator cycle that warmed a resonator by a fraction of a Kelvin.
That warmth was a label. Microwave photons whispering which path to the world. They add shielding, reshape pulses, and the burst dies. The note reads like a slit entry. Breath killed coherence, now in cryogenic slang. Why this matters beyond lab toys is simple. The paradoxes are performance specs. Interference is throughput, entanglement is bandwidth, decoherence is loss, measurement is I/O. The math that made you uneasy about pasts is the engineering that builds futures. And that swings the camera back to us. If we're the architects of correlations, the meaning we drag from these machines will say as much about us as it does about electrons.
What the double slit really says about us. Stand with those slits long enough, and they start pointing back at you. The stripes aren't a letter from the universe saying you matter. They're a mirror for how you ask questions, how your instincts cheat, and how careful work beats intuition. We're tuned for solid things with single paths and tidy stories. Quantum mechanics keeps telling us, your pictures are small, your questions decide what you can learn. Agency lives in hardware, not in wishing. You don't will outcomes into being. You wire couplings that either protect indistinguishability or smash it into records. A polarizer angle is a question, a coincidence circuit is a question, a vacuum pump is a question. The world answers with dots and counts that follow the math you baked into the apparatus. That's not deflating, it's clarifying. You're not the magic. You're the architect of what can interfere and what must become a fact. Our hunger for stories nearly wrecks us here. We want the particle went left or the particle went both ways. But the clean version is colder and more generous. Amplitudes evolve along alternatives. If nothing labels them, they add. If anything labels them, they don't. Observation is just a shorthand for labels leaving the system. It's humbling to replace I looked with air molecules scattered. But it's the correction that turns paradox into design. There's a social lesson in the physics. Objectivity, what we call shared reality, isn't a mystical property, it's redundancy. The environment copies records in many fragments that lots of people can sample independently. That's why a chair stays put for everyone, why a cloud chamber track waits for whoever walks in, why a detector click doesn't need a witness. We agree because the room already holds the evidence 1,000 ways. There's also a moral in the engineering. Decoherence is ruthless and patient. It's a whisper that wins by 1,000,000 repetitions. So you learn to be ruthless back. You darken lamps, tame pumps, quiet floors, gate heaters, route cabling, and count stray photons like a miser. You teach young hands that close enough is a lie. The universe won't bend for your schedule. It will bend for your discipline. The double slit also tells you what not to say. Don't use observer when you mean detector. Don't sell mind over matter when the only lever that moved was a Hamiltonian knob. Don't promise time travel when the only trick was a joint question asked at the end. Good language protects good thought. Sloppy language is a leak. It labels what you were trying to keep clean. Interpretations become personal, not because data change, but because temperaments do. Some people want one wave that never breaks. Some want one world with a rule that picks. Some want trajectories. Some want bets. The lab is agnostic and strict. It rewards the interpretation that keeps you careful and honest and gets you back to your screws faster. The rest lives in the part of your head that needs a bedtime story. Still, there's wonder left that doesn't sugarcoat. It's in the first faint fringe after hours of noise. It's in a histogram that grows teeth when you sort it right. It's in the near silence of a cooled cavity. It's in the relief when a notch filter kills a phase wobble at 18 hertz. It's in the shared grin when a room of people sees the same tiny ridge and knows it's real. That wonder isn't mystical. It's earned. There's a human cost in that earning. Months can vanish to a gasket that creeps. A grant can hinge on a decimal place you didn't get. A student can stay too late for a fringe that won't come. The antidote is the same arithmetic we've been preaching. Redundancy, share records, document hard, let many fragments carry the truth so no one person has to be the whole ledger. Objectivity is a team sport. The open loops are honest ones. Gravity might still nudge superpositions off the stage. Massive fringes might stall at a scale that isn't just engineering. Friend labs might teach us how far coherence can wrap around memories before redundancy wins. If a crack shows, we'll see it in lost visibility. We can't blame on leaks we've already killed. If no crack shows, we'll keep using the same tricks to build clocks, codes, and sensors that make daily life sharper. So what does the double slit really say about us? That our first pictures are small and fixable. That humility beats certainty when dots don't match slogans. That meaning grows from careful hands shaping alternatives, not from special eyes willing outcomes. And that the deepest respect you can pay reality is to ask clean questions and accept clean answers, even when they bend your instincts.
Meanwhile, the cold promise from the start still stands. Reality doesn't shapeshift because you watch it stiffens or softens because you built the conditions that decide what can interfere and what must leave a mark. That puts you in the story without making you the author. It's a better
Role than the myth. Not sorcerer, but builder. Not center, but co-worker. And that's enough. Resolution and broader meaning. That's the turn. Reality isn't waiting for you. It's waiting for the question your apparatus writes into it. If you want the wildest test beds, levitated giants, friend labs with memory qubits, gravity's rumored bite, watch the next video cued here. Subscribe for more true, freaky stories where careful choices make the universe show its cards, one interference term at a time.